It's about at this point in the semester when, if you've been paying attention, you recognize that there's a story that we've been crafting. We started off with saying that math is this model of logic. It's our recognition that the things that we know should make sense, we can not only use that as evidence for convincing people of an argument or for changing our perspective strategically, but that we can actually extrapolate beyond our common sense using symbols. So we may say that it's perfectly reasonable for us to talk about the distance between two numbers, but if we use absolute values, now all of a sudden we can make the idea of finding the distance between positive and negative numbers so much easier than just having to count and reason through them individually. And that if we're able to expand on and say that we can ratio numbers, or that we can compare them from their constructions, that we can come up with numbers that would be boggling to the mind to actually create, like pi. Where did it come from? How is it so big and complicated? We can acknowledge that these numbers exist, whether we know exactly what they are or not. And then we can go from there and to say, okay, well, now that we have the idea of numbers, how are all the different ways we can represent numbers? Can we represent it with pictures? Can we represent it with shapes? Can we do different things like squaring it? Can we talk about taking these expressions and transforming them into different perspectives? Can we talk about simplifying them or making them more complicated? Can we relate them to other pictures that would give us procedures by which we can manipulate them reliably? And then after we've got a good understanding of not only numbers, but the behavior of numbers, we can express those using variables. So now we've gone from numbers to different types of numbers, to variables that represent all types of numbers, to now being able to connect different amounts of numbers to other numbers in the form of equations. So now we've gone from numbers to representations like expressions to equations. And now we're going to take this one step further into the idea of functions. Now, the idea of functions is a very math word, but it's actually quite new. In fact, Harvard University is actually older than the idea of functions. They were invented in the late 1600s as people were getting comfortable with this idea of graphing. That again, Rene Descartes had just figured out this model of, again, how is it that I can connect two unrelated things, a question and an answer, an input to an equation and an output from an equation into a common picture. Now, the idea of functions was to try to take this picture that Rene Descartes had come up with and to be able to speak about these pictures a little bit more precisely. So, for example, if you wanted to know the function of the number 2, then you would be saying, okay, well, I have a number 2. If I put a number 2 into an equation, or I try to manipulate it, what is number 2 going to get me? What's its purpose in this equation? What's its end goal in all of the things that are happening? So we would start to talk about the function of a number, and that very quickly became the idea of saying, well, all of these equations that give us just one outcome for any given question, then these are equations that function. I like to think of them as business equations, right? And when I worked in business, it was very common that you'd be asked questions all the time based on, the questions from the day, what was happening around you, and what we're going to do next. So a common thing would be, how many people are we going to pull in today to help us output all of these boxes? And you had to give an answer to the boss. You had to say that we're going to need to pull in 12 people. You couldn't say, maybe we'll need to pull in 12 and maybe we'll need to pull in 15. It was you had to have a number. If you didn't have an answer, then this business wasn't allowed to function. There wasn't a forward direction that you could put everything in. So there's always one question, and if you could find one answer to that question, then you had a functioning model. You had a functioning mathematical model, an equation. So let's go ahead and jump into the notes packet, and I'll show you a little bit more about how we can determine whether or not our models are functioning models, or whether or not they're just relations connecting two different things together. So let's do a little bit of a recap here. So what are the things we've learned so far? We have expressions. Expressions are any way of writing down something that we have in our mind, right? So I could express the idea of three objects using a symbol. I could do it just like this. We could call that 3, and I would say this has in it the meaning of the quantity of not one object, but another object and an object on top of that, all expressed right here. In fact, another expression could be of 3, could just be 3 tally marks next to each other. Or sometimes we could just talk about it as unknown objects, like x plus x, right? Where if x is 1, then this entire expression is equal to 3. I've got x plus x, where x is equal to 1. This would be expression. In fact, this would be what we would consider an algebraic expression. Algebraic, meaning that this was a notation where at any given moment I could use the structure with a different input, and I could think about the exact same behavior without having to be specific about the number that we are manipulating. Okay, what about equations? We've talked about equations. Equations are going to be any time that we can equate two different things. In other words, we can determine they are equal. So this would be something like 3 plus 4 equals 7. Notice again, we've got a difference in perspective. We have 3 objects, and then we have 4 objects separate versus 7 objects together. This is an equation. It equates these two ideas for us. Or maybe a better way of thinking about it would be something like 200 divided by 400 is equal to 1/2. Now this is an interesting equation because on one hand, you're looking at this and saying, well, if I have $200 and I divide it amongst 400 people, then it's as if every person gets half of a dollar. But you could also look at that and say, is 50 cents really the same idea as saying take $200 and divide them amongst 400 people? I mean, it's a difference in perspective. And so you're equating these two perspectives as saying, okay, I can understand how the same scenario could get me both of these perspectives. Okay, well, what about relations? Relations are anytime that I'm trying to relate two things. So for example, a family tree is a very common relation. This is a mathematical model. It's a model of logic. It's a model that connects me to my parents, right? It connects me to my sister. So a relation could say that I have me going to my sister, and this would be a relationship saying that I'm able to take me and I'm able to relate it to somebody else. Just as similarly though, you could say that I'd like to always, whenever I have $500, I would like to spend all of my $500 so that I have no dollars left. This would relate the number 500 to 0, meaning that I started with 500 and I know that whenever I get to $500, I'm going to go back down to 0. This is a relation. So we've got this idea of modeling logic, and you really can be quite liberal with the idea. How are all the different ways that you've ever related to something in your life? Could you have represented that with a model? Could you call that mathematics? And I would argue absolutely. Now we do have this idea of function, and we've talked about this one before, and this is the focus for today. So the idea of function says that I'm going to ask a question, and I will always have, at most, one answer. Okay, so that's what we're going to determine as a function. So the definition of a function is any relation between inputs and at most one output per each. So let's take a moment and again, let's recontextualize this. And if you want, this is an important thing for you to do in your notes. Just put yourself some notes and write this in your words after I explain this to you a little bit. So the idea again being, all I'm doing is I'm going to ask a question, or I'm going to start with something, and I will know that my model is a function if I'm able to always have at most one answer, just like in a business. If I say, what are we going to do on Tuesday? There cannot be a, well, we could, or it's going to be, we do, if we're going to function appropriately. Okay, let's look at a couple of pictures here. We'll do some models. So for example, we're going to determine if these are relations or functions. So in this picture, it looks like we are relating Phoebe to a height of 5 foot 5 inches tall, relating Amy to a height of 5 foot 5 inches tall, and then Katie we're going to relate to 3 feet 1 inches. Oh, maybe not tall, maybe just an inch of, I don't know, maybe string length. All right, are these relations? Yes, they are relations because I am relating one thing to another. So is this a relation? Absolutely, it is a relation. Check. Is it a function? If I ask you a question, do you have at most one answer? So for example, if I ask you, what is Katie being related to? There is only one answer. It is 3 foot 1 inch. There is no ambiguity. If I say, Katie, you think 3 foot 1 inch. So that means that it is a function. So we'll put a little function here and give it a check mark. Here's a relation and a function. Perfect. All right, let's take a look here. I have 2 and it is being related to 20 and is being related to 40. I have number 4 and it's being related to 40, and I have the number 3 and it's being related to 30. Is this a relation? It is a relation. Again, I am relating one thing to another. So I would say, yes, it is a relation. Is it a function? Well, let's ask. If I ask you the question 3, for example, is there only one answer you could give me? You'd say yes. If I ask 3, it goes to 30. No ambiguity there. What about 4? If I ask you the question 4 and I say 4, code 4, what are we going to do with code 4? You'd say we are going to do 40, right? If I said, what about code 2? Or we're asking the question, what about 2? You would say 2 is going to give me, well, 40 or 20. And that's the breaking point. It cannot be a function if there isn't a clear line of attack, if there's not a clear outcome that results from this. You can't have 2, no ambiguity. So is it a function? No, this is not a function, because I do not know exactly one answer, at most one answer, for the question of 2. Okay, we're starting to get the idea of this. Again, this is how businesses operate. If you want to have a good plan, that means when thing happens, then other thing will happen. That is a function. If you imagine at a hospital having a plan for, like, code blue means one thing. Everybody knows exactly what that means. That is a functioning system. What about over here? Here we have a number of different points. So these are all different points. I can tell they're different points because they're all collected in a set, which means I just have a pile of points, and I'm going to be looking to say, okay, what is my question? What is my answer? First, these are coordinate points, meaning that I am connecting or relating the number 3 to the number 7. Here I'm relating the number -3 to the number 2. And so the question is, do I have any place where if I ask a question, there's ambiguity? So if I ask, for example, the question 3, is there ambiguity? And you would say, well, I ask 3 here, I get 7, no problem. If I ask 3, it doesn't appear here, it doesn't appear here, it doesn't appear here, and it does appear here. So 3 gets me -4. Do I have ambiguity? If I say 3, do you know what the answer is? And again, the answer would be no, you don't. It could be 7 or -4. That's not a function. It's a relation. It definitely connects 3 and 7 and 3 and -4, but it's not a function. It's not something that would be unambiguous. All right, what about this one here? We've got a coordinate plane. So a coordinate plane, again, as a recap, connects questions or inputs with answers or outputs. So let's see what we can figure out here. This has an input of -4, and we say, if I put in -4, what is the height that will result? What's the y value? And you'd say, no problem. The y value that would result would be 5. And if you wanted, you could even write it in the same way as part C up here, or the one that we did before. So we could write that as -4, comma 5. It relates -4 to 5. And here I would relate -2 to 2. Here I would relate 1 to 4. And here I would relate 1 to -2. Do I have any ambiguity? Well, I'm going to leave that one for you. If you have questions, you pull me over and lecture, but this is the question. Is there ever a time where I'm asking a question, in other words, I'm giving you an x value, and I'm saying, I don't know exactly what my output will be. In this case, what my height will be, either up or down. Is there a time where I don't know exactly if I'm going up or I'm going down, and how much it is? You can only have one answer if it's a function. All right, finish that question, put that one in your notes, and explain yourself in this area right over here. Why is it that you made that call? So we're getting again the idea that function is just one more layer on top of the logic. We started off with numbers, we moved from numbers to expressions, we went from expressions into equations, we were going from equations into relations, we're going from relations into functions, right? All of these kind of nesting in each other. But of course, if we're trying to connect questions and answers, even if they're unambiguous, we can do that when we're working with equations here. So notice that what we're going to be playing with is looking at some structures like this, and saying, is this a structure where if I ask a question at any given point, it will give me only one answer? And this is really useful because, again, these structures may be the ones that we sometimes want to use when we're trying to plan ahead in certain situations, like business, where you would very much like to know what to do at any given point. Or if you're trying to make a call about finances, sometimes these are much more useful. Okay, so what can we do? I would recommend that perhaps we look at this in the same light that we had looked at some other ones, which is let's try to get it where we have y equals. And if we can restructure this as y equals, what that really is saying is that my answer is. If y is my output, then we're saying y meaning my answer, and then equals meaning is. And then all we have to do is solve for the right hand side, and we would know what my answer is at any given point. And that might be a nice way for us to find out if we ever have any overlap. So let's go ahead and readjust this if we can. I need to get y alone, so I'm going to subtract 3x from both sides. So I'll subtract 3x over here. That's going to get me negative 2y equals negative 3x minus 12. Okay, and then from here, let's divide by negative 2. So that'll be y is equal to negative 3 divided by negative 2 is 3 over 2. X, and then negative 12 divided by negative 2 gets me a positive 6. Okay, great. So here we have a linear equation. In fact, I could have recognized it's a linear equation before because all I had was numbers times variables. And down here, I've just restructured it into what looks like slope-intercept form. So we could graph this if we wanted. This would be where I start at a value of 6, 1, 2, 3, 4, 5, 6, and then every time I take, it looks like 2 steps over, because it's rise over run, so my run would be 2. Every time I go 2 steps in my run, I'm going to go 3 up in my rise, 1, 2, 3, and that's going to be my next point. All I need is 2 points to create a line, and so there we have it. That's going to be my line. Now the question is at any given point, do I have a question, some value on my x, that would go up or down to one and only one answer in my y value? Is that going to be true any place I go? And I would say, yeah, it looks like it will be. Even if we go over here, it looks like I'm just going to go down to a different point that's on the line. And so at any given time that I ask a question, and my question could be something like positive 11, right? Where's 11 going to get me? You'd say on the line, 11's going to get you, and you would get me an immediate answer. In fact, we could even play with that over here. We could say that'd be 3 over 2, and we could plug in 11 plus 6, and we could solve all of that out, okay? And that would be our y value. But what we've just done here is we've recognized that this is more than just an equation. This is a function. This is a function where the answer is always determined by an input, and it's always unambiguous. So why don't we communicate that? Let's model our logic a little bit better. In fact, a lot of times what people will do is they'll write this with a brand new title, and they'll write this with an F and a parentheses with an X in it, and they will say this is equal to 3 over 2 x plus 6. And what they're really saying by this is an entire sentence of information. Check this out. This F says a function of x. Now it's important to note, this is not multiplication. This is an important moment. Don't read this as letter by parentheses of letter equals multiplication. No, this is a different thing that we're trying to communicate here. It's just a notation that people use to say that I have an x value, some kind of question, and I'm going to put that into a structure, and I'm going to label that structure as f. And this can be very useful because if I'm going to be talking about many different equations, now instead of having y equals a line and y equals a parabola and y equals a circle and having y's all over my paper, I can say I've got a function of x called f. And if I wanted to have another one, I could say I have a function of f called g, and I could call it g parentheses x, and I could label this with whatever letter I thought was going to help me remember exactly what I was doing with this model at any given time. It has an even better benefit of saying now what I can look at is, for example, instead of here where I just plugged in 11 and I would have gotten a y value, but if I'd plugged in 4 I would have gotten a different y value, we can be a little bit more creative with our notation and say something like f parentheses 11, and what we're saying here is it's now a function of 11 called f, right? Function of 11 called f. And so we're trying to ask ourselves, what is the function of 11? What is the purpose of 11? What does 11 get me? And you'd say, no problem. If I put 11 into this line, this would be 3/2 times 11 plus 6, which would be what? I think it'd be 45 over 2. And so you'd say, there you have it. That's the function of 11. The function of 11 is to get me a value of 45 over 2. And that's the only purpose that 11 ever has, is to get me 45 over 2 in the function of f. And we would go up here in our picture and we'd label this and say, here you have it. This is f. F is my line. Kind of better than just saying y. Now I've got f. I can be very specific. I can put many, many things on the same picture, and so long as I call them different letters, I can keep track of them a little easier. This becomes really useful in the next example. Let me show you. So here, I'll section off a little bit of space here. This one here you should recognize as being the equation of a circle. And so if that feels a little bit weird, let's try to solve it for y the same way that we're looking. So this would be what? Y squared equals, and then I could subtract the x plus 3 squared to both sides. That would be, let's see, 16 minus quantity x plus 3 squared. And then you could square root both sides. You say y is equal to plus or minus the square root of 16 minus x plus 3 quantity squared. Now let's ask ourselves, is this a function? Well, no, it wouldn't be a function. Do you know why? Read it off again. Y equals the plus or minus of a bunch of stuff. So again, take a number like 11. If you put a number in here and you added it to 3 and squared it and then did 16 minus that number and you square rooted that, all that would be fine, but then you'd come to a decision point where you'd go plus or minus and you'd have to make a choice. And at the moment that you make a choice, you've got some ambiguity. It's not a function anymore. That's kind of crazy that you can sometimes just look at it without the picture and you just interpret what's happening. You say, if I ever have to make a choice, it can't be a function. However, you could be a little creative here. And you could say, you know what? If I have to make a choice, then what if I always chose the positive? Would that be a function? Yeah. So here's what we'll do. We could break this up into two different ones. We could say, let's call it, we already called one on our paper f. Let's play it with some other numbers. We'll call it g, because y, that's the letter that comes after f. I'm not creative. So we'll say g of x, we could call the square root of 16 minus x plus 3 squared. And then h of x, because I'm again just going through the alphabet, h of x would be the negative square root of 16 minus x plus 3 squared. That would be, each of these would be worthy of getting this label, this title, this permission of being called a function, because once I have no ambiguity in it, I can label it in this special way that says I have a title for it. I know exactly what it's depending on, these x values in here, and now I can label it on my picture. In fact, if you wanted to draw a picture, we could do that real quick and we could see exactly why it's not a function, or why it wasn't a function before, but it is later. So the first way we were looking at it was a circle with a center at an x value of -3, 1, 2, 3, and a y value of 0. And it had a radius of 4, so that'd be 1, 2, 3, and 4 would be the radius. So this would be the circle, something like this. And we could say, is this a function? Well, we already knew the answer. It was not. And the reason is if I ask an x value question, I don't know if I'm going up here or if I'm going down here. And if I've got that ambiguity with any question and I don't exactly know what my answer is, it can't be a function. But you could look at a circle as being the combination of an upper half circle and a lower half circle. And if you wanted to just think about one of the circles, half circles, or the other of the half circle, then that absolutely could be a function independently. Each of these could be functions. So you get to kind of just play around with this idea of what is it to be a function, what is it not to be a function. It's if I am going up or down a specific amount, depending on what the question is that I'm asking. And sometimes if something's not a function, I could be a little bit creative by turning it into a function or a couple functions or a bunch of different functions, so long as I'm making sure that in the very end, whichever one I'm talking about, I have a specific question, it gets me a specific answer. Okay, so for any functions found above, find a function of 4. So what does that mean? Notice here the notation, f parentheses 4. So f parentheses 4 means find the function of 4. And so let's do that in each of our different pieces. We'll do it for A. So the function of 4 for our line at the top could have been, well, let's copy it down first and I'll show you the parallels. It's kind of pretty here. So we'll start off with the function of x. If you remember, f of x was what we called our line. We were able to give the special title of function. So if f of x is 3 over 2x plus 6. That meant that the function of every x value was to get plugged in here and give me one and only one answer. And if I want to know the function of 4, for example, then I could say, no problem. The function of 4 is to say, well, if I plug in 4, what do I get? And you'd say, no problem. I'd take 4 and I'd multiply it by 3/2. That would get me 6. And then I'd add 6 to it. That would get me 12. And so the function of 4 in my f function is to get me 12. What about here? What about in my g function? You'd say, no problem. G of 4 would be square root of 16 minus 4 plus 3 quantity squared, which would get you, let's see, 7 squared, which would be 49, and I don't think that would get you an answer. So there we go. No solution for that one. Plug that in your calculator, it won't work. But again, is that still a function? Yes, because I just said it has to have at most one answer. This is absolutely an answer, or at most, one answer. It has no answers. So what happens? Nothing happens. That's perfectly unambiguous, still a function. And the same thing would happen if we did it in this h function, right? H of 4 would mean plug in 4 into the function titled h. And you can see these parallels here. Notice I had an x and it was a function of x. And when I replaced x with 4 over here, I replaced x with 4 everywhere I saw it. And when I replaced x with 4, I replaced x with 4. And when I replaced x with 4, I would have replaced x with 4. So this is a really a much better notation than just saying y equals. Y is depending on my x. Y is a different y every single time I ask a different question. Here, at least I get to keep track of not only what is my question, but what am I doing with that question to get a really good answer. Okay, so to wrap all of this page up, what is the definition of the independent variable? Well, think about the word. An independent variable, just like an independent person, is somebody who can operate without being influenced. So an independent variable is a variable that is not affected by another. And the easier way to think about that one is just to go back through what are the two different variables we've looked at. We've looked at still x and y. Notice again, f, g, h, not variables. They were titles. They were titles of the equation, the structures we were asking about. You could think of them like computer programs. We had a computer program called f, where I put a question into it, and then f did its magic, and then it gave me an answer. And for some other ones, g was a program. I put a question into it, it did its magic, and it gave me an answer. So what was the thing that I was not affected with? What was the thing I was starting with that I couldn't be influenced on? It's your question. So a variable that is not affected by others, usually that's just your x value. So your independent variable is the one we're starting with. I have a question, no one's going to change my question, I'm going to put the question into the program. What is the dependent variable? Well, that is the thing that's going to be affected by another value. So you'd say it's a variable that is affected by another. And you can again think back on the story and say, well, what's going to be affected? Like what if I always want to know the answer to my question, right? What's the answer the computer program's always going to give me? You'd say, well, that depends on the question you ask it. Well, if it depends, then it's affected by another. So the affected value is your y value. So write this is kind of the proper notation here, but I want you to take a moment and I want you to put a little note in your notes that's you speaking to future you. What's the way that you think about this one? So we've spent enough time playing around with the ideas and really getting comfortable with functions that now we want to find a way to kind of expedite the process. Is there a way that we can determine if things are functions just by looking at their picture, their graph? Because after all, that's supposed to have all the information of the equation itself. So let's take a look here. Are the following functions? Well, again, we're going to be looking and saying, well, I'm going to ask a question. I'm going to put in a independent variable, which is x, and I'm going to say, what is my dependent answer? And you say, This one seems to give me one answer for this question, another answer for this question, and as I go through any question, any x value that I start with, it's going to get me one at most answer. Over here I could ask the question and it just doesn't give me an answer. That's still fine, unambiguous, and you'd say absolutely this one is a function. So we'd say, is this a function? Yes, absolutely, give it a nice little check mark there. What about over here? Is this one a function? You say, I don't know, let's ask some questions, and say I could ask some questions here and I would go up or down to my question. What about this one? Number 2. Ooh, what is the answer to the question of 2? I would go up until I had an answer. The dark circle here would say, yeah, that's where I have a point. So that could be my answer. Is it my open circle? No, open circles, if we remember even back from interval notation, those were values that weren't included. Those are values that weren't there. They're not actually there. They're just reference points. So that one's not going to be my answer. This is my only answer. So I've got one answer, and then everywhere else only has one answer. Again, this is a function. Anytime you ask me a question, I'm going to be unambiguous about what my answer is. Even at that one little weird little spot there with the number 2, if I say, what is my answer for the question of 2, you'd say, the only place that I get an answer is wherever this closed circle is. So sure, gives me only one answer. What about the next one? So I'm going to put in a question of x values, and I'm going to say, I am curious about what my y value is. Do you see how there's 2 y values here? Like there's another one down here. I'll put that one in pink. So if I ask you the x value question, I put in the independent variable here of x, and I say, what does putting in this starting spot get me? You would say, well, I could go up or down. Well, if you can go up or down, then I don't have a clear answer. It's not a function, not a function. So I'm going to say, is it a function? No, not a function. And this is where we start to get a little bit of a shortcut. Notice the shortcut. All we're doing is looking up or down all the time. And so if I ever cross my graph more than once, like here, where I cross it more than once, that must be a place where I have ambiguity. Everywhere else, if I just draw these vertical lines going through, I only cross once. Even over here, I only cross once. We call this the vertical line test, and this is a nice shortcut to be able to determine if things are functions. So what is the vertical line test? I'll leave you the opportunity to be able to write it in your notes right here, but it's exactly what we just explored with above. Draw a number of different vertical lines going across the graph. Don't make them angled, don't make them sideways. We want to keep them nice and vertical. And if the vertical line test says that if I ever cross more than once, then that's a nice signal to us that there must be a place where if I ask a question, I will get more than one answer. Let's talk through a couple of other ways that we can categorize and classify functions, because as you can see, there's lots of different pictures we've been able to play with. We've been able to play with all the way back at the beginning. We played with functions that looked like mapping different objects. We played with functions that looked like piles of points. We played with functions that looked like points on a grid. We played with functions that look like entire graphs. We played with functions that look like equations. We played with functions that look like crazy graphs. What are ways that we can kind of talk about all of these if we're going to be having discussions? Well, one way is by the domain. And I like to think of domain, pulling on a little bit of Disney trivia. If you ever watched The Lion King, essentially there's a scene where the baby Lion King is held up across the savannah, and later he is told that wherever the sun touches is his kingdom. And I like to think on this because whenever I think of the domain of something, I like to think of just that scene from Disney's Lion King, where it's everywhere the sun touches is his domain, his kingdom. And so when we talk about the domain, if you imagine like a graph, we'll draw some kind of graph. You're looking for all of the places where if the sun is up here and it's shining its light on down, where is it that this sun kind of touches? It's going to touch here through the graph, and it's going to touch here through the graph, and here through the graph. It's everything sideways that is a valid question for me to ask that will get me some kind of answer. And so we'll write down a technical version, but then you can keep this little picture and write yourself some notes over here to make sure that you don't forget. But define the domain of a function. It's all questions which get an answer. Now we can make this a little bit better. Instead of questions, we'll say it's all independent variables with dependent variable solutions. Now, when it talks about the range, you could guess that this is probably going to be the other direction. Like if you're trying to talk about, the range that you could throw something up in the air, this is going to be how high or I guess how low this all could reach. So the range is going to be all possible answers to our question, or in terms of our picture, what we're really looking for, I'll change the color here to green, is we're looking to say, if I instead was shining my light on sideways, where would that shadow be cast? And you'd say, well, here in my yellow, I had shadow everywhere here. For the green, I would have shadow everywhere from my highest value down to my lowest value. And so in terms of our range, which again is all answers to questions, in other words, all dependent solutions, now, the last thing we always want to do, again, as we're working through mathematics, is just try to make it simpler and simpler where we can get to these correct answers in our mind without having to do so much work where we're taking up time and drawing pictures. Pictures are great for us to build up understanding, but they're unnecessary once we have that understanding. So instead, let's see if we can just describe what some of these domains will be for different equations. And so now in the future, when we look at these structures, we'll have already given them plenty of thought, we'll have gotten nice and comfortable with them, and we won't have to spend so much time drawing pictures or considering all the different scenarios. So for example, let's take a polynomial. We've looked at polynomials before. Let's recognize exactly what they are again. They're numbers, like here's a0. A0 is just the first number, what we call a constant. And then we have a1. That would be another number. We would call that a coefficient because it's in front of a variable. And there would be a bunch of other coefficients going all the way through this. But all it is coefficients, in other words, numbers, times variables to a positive power. So I have numbers times variables to a positive power. So this would be like your x squares, these are your x cubes. These are your shape equations, right? These are anything that kind of look like they might be similar to the length, width, height kind of shape pictures that we've been playing with so far. Now the question is, how do they know that the domain is -infinity to infinity? And notice again, this is an interval, right? This isn't a point over here. We use parentheses. We've used parentheses in a lot of different ways in this lecture. We use parentheses when we were talking in our interval notation, when we're talking about points on a graph, when we're using it with function notation. So it's all about trying to pull out the meaning. Here, a domain is all of the x values, and we know how to describe piles of x values using either set notation or interval notation, and the only one that has infinity would be interval notation. So this is an interval. This means everything between our negative infinity number, which doesn't exist, it's just all the negative numbers with no lowest bound, to all of the positive numbers with no highest bound. These are all numbers that have valid questions into this structure. Now, why is that? Well, here's the way that I think about it. Is there a number that you could not add to another number? Think about it. Is there any number that would cause conflict with? And I would say no. Well, that's all that we're doing when we look at a polynomial that might have a little number being added at the end. Here's a number. Here's an x value that I could be putting into that equation, and I could be multiplying by another number. So I guess the better way of asking this is, if I give you an x value, which is my question, and I have you multiply it by a number, and then I have you add that to another number, are you ever not going to get an answer from that? Are you never going to get an answer to that question? You'd say, no, I can always take an x value and I can multiply it and I can add stuff to it, and that always gets me one and only one answer. You'd say, okay, well then that's no problem. Well, what about squaring it? Could I ever square a number, and would that ever be confusing? Well, even if I do negatives, like -3 squared gets me +9. That's pretty cut and dry. If I cube something, that's even cut and dry. So no matter what power I raise it to, I still get a cut and dry answer. And I can always add those numbers together and I get a cut and dry answer. And I can multiply numbers and I always get a cut and dry answer. And I'm always going to get a cut and dry. I'm going to get one and only one answer. Well, if that's the case, then the domain, the pile of all valid questions, must be all valid numbers. Any number that I put into here, I'm either going to square it or cube it. I'm going to raise it to some kind of exponent. I'm going to do some multiplication and some addition. But when all is said and done, I will have one and only one answer. So as long as you have only multiplication, addition, and subtraction happening in this structure, in other words, a polynomial, then you have a function. It can be described with the proper function notation of giving it this f in parentheses x to call it a function and to say that it's depending on a value x everywhere throughout the structure. Good. So that I want you to see if you can pause the video right now, recap why it is that polynomial functions are functions down here in this space right here. Now the next question is about rational functions. So here we have again, rational functions, as a reminder, are polynomials where I take some kind of polynomial, and you can see that again we're just using labels here. So I'm going to call some kind of polynomial g. This is a polynomial, a function that is depending on x, divided by another function called h. So this isn't multiplication that's happening in the numerator. This isn't multiplication that's happening in the denominator. This is a function. This is some kind of program called g, where I ask it a question called x. So I put in a question x into my program g, and it spits out an answer. I put in a question into my program h, and it spits out an answer, and then I divide those two answers by each other. That's the way you can think about this. And it's almost like I'm building one program with two other kinds of programs here, right? Because then that all becomes my function at the very end. I'm trying to think of what an example of that would be, but maybe it's just like the videos that I record here. I record them on one software, I edit them on another software, and then I put them into YouTube so that you all can have access to them. So that's nothing more than me asking questions or putting things into one program and then using that program in another program and using that program in another program. And at the very end of that, I have, well, we hope, one and only one result. And the question here is, in this structure, do I get one and only one result? Well, again, I like to ask this in a little bit of a simpler statement. Let's look at what's happening. I have nothing on the top except for a polynomial. And a polynomial, as we said, is multiplication, addition, and subtraction. I already have established that there's no problem that I ever could encounter with that. I will always have one and only one answer. No problem. On the bottom, I have the same thing. So far, the top doesn't have a problem, and the bottom doesn't have a problem. And there's division between them. So the question I have is there ever a time where you can't divide by a number? We said there's no time where you can't add by a number. There's no time you can't subtract by a number. There's no time you can't multiply by a number. Is there ever a time you can't divide by a number? And hopefully you're saying, yes, you cannot divide by 0. So that would be the only time where this would not be a function. It'd be a function not there because that would not give me a solution. It'd be undefined. And you can see right here that that's exactly what we have written in the domain. The domain is all real numbers such that h of x, the bottom thing, doesn't equal 0. So long as the bottom isn't 0, anything else that I want to put in here is totally going to work. But if the bottom is 0, doesn't work. So I can't ask that question. You're not going to get an answer. All right, root functions. So here we are. Now we're just kind of going again through all of the different models we played with. So I have a function. That means I should get one and only one answer. I need to figure out what the questions are that I can ask here. And then I'm going to be doing it a root, an nth root. So some amount of finding groups and then pulling those representatives out front. And I'm doing that for, so we got some kind of function here. So here we are. I've got a function. I'm going to be doing a root to it. Is there any time that this is going to break? Is there any out of bounds values here? Well, again, the question I would ask is there anything that you're not allowed to take a root of? Can I do a square root, for example, of 0? Yes, that would be a 0. Can I do a square root of a negative? And hopefully you're saying, no, you cannot do a square root of negative. And I would say, perfect. So if you're doing a square root of a negative, you're going to have a problem. In fact, if you're going to do a fourth root of a negative, you're going to have a problem. If you do a sixth root or an eighth root of a negative, you're going to have a problem. Anytime you do an even root of a negative, you're going to have a problem because you're going to be looking for pairs of numbers that multiply to a negative, and that just never happens. So that's a place where we go out of bounds. Oh, and look right here. That's what we've described right here in the domain. If n is an even number, in other words, if I'm doing a square root or a fourth root or an even root, if I'm doing an even root, then the domain is the solution to the inequality g of x is to be greater than or equal to 0. That was a little hard. What does that mean? It says that the domain is all numbers such that g of x is bigger or equal to 0, which would make sense. If g of x is bigger than or equal to 0, then I'm only doing a square root of 0 or bigger numbers, 0 numbers or positive numbers, and those are perfectly fine. So we see where we get the answers from. So if I have a square root or any kind of even root, then the inside of my root has to be positive. That's all that it says right here. Now, if n is odd, that means I'm doing a third root or a seventh root or a fifth root. So I'm looking for groups of odd numbers. Well, that allows us to again say it could be positives or it could be negatives. For example, a third root of negative 27 would be fine. It would be negative 3. So I can do odd roots of negative numbers. I can do odd roots of positive numbers. So if n is odd, the domain is the set of all real numbers, right? So long as whatever's on the inside is actually a legitimate question. So take a moment, draw or write down here a little interpretation to yourself to help you remember in the future what it is that we're doing here. Because all we're doing is we're saying, what are the questions I can ask? Those would be my domain. If I wanted to know what answers I could get, that would be my range. If I wanted to make sure that anytime I ask a question, I get one and only one answer, that would allow me to say, not only am I relating my questions and my answers, but I'm relating them unambiguously. In other words, through the function